Hello, everyone. So today I want to talk a little bit about what it means for a graph to be connected. So when we introduced graphs in this class, we said that they're really these mathematical gadgets that allow us to take a finite set and talk about which elements are connected. So let's look at these two pictures here. So I have two graphs, G and G prime. And if you think about it, I think most of us would probably say, well, it looks like the graph G is connected, and it looks like the graph G prime has pieces that aren't connected to each other, right? There's the triangle XYZ, that single edge UV, and then a vertex floating all by itself. So I want us to think a little more deeply about what it means for a graph to be connected. So I think what we're thinking about is that if I take the graph G and I look at any pair of vertices, I can walk from one vertex to another along edges and get anywhere I want. So for example, the vertices A and B are connected to each other by an edge, but I can also say that I can get from A to F by walking along edges. So let's say we can walk from A to F along edges. And I'm going to do this in blue, where I might start at A and I can go to B, to C, to D, to E, to F. So I've walked from the vertex A to F. But in the and then in the graph G prime, it's not connected. And in this graph, we cannot make a similar kind of walk from, say, a vertex X in the triangle to the vertex V, because there's no edge connecting the triangle to the vertices U and V. Okay, so let's formalize this notion of a walk and look at some definitions. So this is in a worksheet that I have for you. And in this worksheet and in our textbook, these definitions are all for pseudographs. And that's really partly because there's a very, very famous example that I'll talk about later in this video, where we need to allow that some vertices are connected by more than one edge. So that's what it means to be a pseudograph. In our textbook, you can have more than one edge per vertex, and also sometimes you can allow loops, but we're not going to deal with loops in our class. Okay, so let's formalize the notion of a walk. Given a graph or a pseudograph G, a walk is an alternating list of vertices and edges where, so there's the start vertex V1, and then the edge E1 has V1 as one endpoint and V2 as its next endpoint. And then the edge E2 has V2 as its first endpoint and V3 as its next endpoint, et cetera, et cetera. Of course, in the book, especially if there aren't multiple edges, it says that usually, instead of really giving this alternating list of vertices and edges, you can just give the list of vertices and the edges are implied. So I'm going to say, usually, we just give V1, V2, V3, ... to Vm plus 1. And the edges are implied. Okay, so like, what does that look like in our example? If I wanted to specify this walk from A to F, I might say it's the walk A, B, C, D, E, F is a walk from A to F. And there are lots of other kinds of sort of things we can define that are more specific than walks. So a trail is a walk in which all of the edges are distinct. So maybe I can take a walk and it would go from A to B to C, back to B. So I could go back and forth along an edge, but a trail is a walk in which all of the edges are distinct. A path is a walk in which all of the vertices are distinct as well. A circuit is a trail in which the first and last vertices are the same. So it's a trail, all of the edges are distinct, and you end up where you started. And a cycle is a circuit in which the first and last vertices appear twice and all other vertices appear exactly once. So that's a lot of different definitions. The ones that we'll use the most in class are paths and cycles, especially, okay? So let's see. In our example above, when we walked from A to F like that, we actually were giving a path, a trail and a path. So this is a trail and a path. Can I see any cycles? Yes, I can. So A, B, from A to B to C to A is a cycle in G. There are no cycles here that are not circuits, but if I wanted to see a graph that has a circuit that isn't a cycle, so this bow tie is a good example. This bow tie. So here, if I do, and let me label the vertices. So A, B, C, D, E. If I go A to B to C to D to E, back to C, and back to A, what I have here, let's see, I think it's a circuit that isn't a cycle. Let's check back at our definition. A circuit is a trail in which the first and last vertices are the same. So the first and last vertices are the same because we started and ended at A, and it's a trail because all of the edges are distinct, right? So this, where I'm going, whoops, I'm going A, B, C, D, E, C, A is a circuit that is not a cycle, okay? And in office hours, we can spend a lot of time exploring this definition, and you'll have homework problems to explore these definitions and your understanding of them. Right now, though, I want to tell you about a very famous problem that sort of and some people say this sort of motivated the beginnings of graph theory. So there was a famous mathematician named Leonhard Euler who lived in a city named Konigsberg that was in Prussia at the time. And let me see, I'm trying to, oh, I know what I need to do. I drew this picture already. I'm going to paste it in. So we lived in Konigsberg, and there were these rivers in Konigsberg, and there were 7 bridges. So you can see the river is the thing that's like this is an island in the center of the river. There's an island. Let me see. There's an island in the center of the river, and then there are 7 bridges in blue. And here, I'm going to make me little brown marks, maybe like this is land, this is land, this is land, and that's land. Okay. And so Euler was walking around town. Notice walk. And he was wondering, if I started on one piece of land, could I cross over every single bridge exactly once, so I'm never going to walk over a bridge twice, and end up in the same place as I started. Okay, so can we take a walk traversing each bridge exactly once, starting and ending in the same spot? So this was Euler's question. And let's see how we can turn this into a graph theory question. So I'm going to make a graph, and I'm going to make the graph in pink. Okay, so I'm going to reduce this whole landmass to a single dot. And if Euler starts on that dot, for example, that dot is, I'm going to put a dot on each part of land, actually. That's what I'm going to do. So here's a dot on this piece of land, a dot here, and a dot here. So I really only have 4 pieces of land and 7 bridges. And now I'm going to connect them. This piece of land is connected to that piece of land through this bridge. This piece of land, it's also connected by that bridge. I have these 2 pieces of land connected by these 2 bridges. There's a bridge here, here, and here. So what you see that I have in pink is really a pseudograph with 4 vertices and 7 edges. I'm going to redraw it off to the side. It looks, I claim, like this. And Euler's question is really, does this graph have a circuit using all of the edges? Okay, so translated into graph theory, does the graph or pseudograph have a circuit using, oh, I didn't leave myself enough room, did I? Hold on. Maybe I'll write it up here. I want to ask, does the graph have a circuit using all of the edges? And circuits can't repeat edges, so all of the edges exactly once. And because Euler was the first person to ask a question like this, these circuits like this have a special name, and you can see on our worksheet. We call a pseudograph Eulerian if it contains a circuit using every vertex and every edge, and we call such a circuit an Eulerian circuit. So in office hours, so I urge you to try to do this example on the example on the worksheet on your own. We can talk about it during office hours, and I will post the solutions then via office hours. Part of the whole theme of this course, of course, has been to try to think about what it really means to understand a definition and make it your own, something you really get. So really the process is by generating examples, simple examples to start that you're sure satisfy the definition, and then things that you're sure are non-examples, and trying to understand, okay, so which part of the definition does it fail? And then to start to look at more and more complicated examples. And as you're thinking of those more complicated examples, that's actually one of those points where new mathematics can get created, and that's how research problems come about. Anyway, so later in the week, we will prove this theorem that a pseudograph with at least 2 vertices is Eulerian if and only if it is connected and every vertex is even. Okay, where connected is going to mean, did I write that? Oh, Oh, there it is. A graph is connected if there exists a walk between every pair of vertices, okay? So I'm gonna leave you here with this cliffhanger. Come to office hours and look for more videos later in the week. All right, see you later.